Welcome everyone, today we are happy to have David Marsh, and he will speak about the string Axiverse in 2023. So please, you're welcome to start.
Yeah, thanks very much. I'm very happy to be speaking to you today, and thanks for the invitation. So, see my slide share. Yes, right. So I'm going to be telling you today about the Axiverse in 23. It's going to be a bit of a review talk, and at the end I'll touch on what I think on some new work that I'm doing and what I think the promise for this sort of program is for the future. So the string Axiverse was proposed in this paper that was published in 2010, appeared on the archive in 2009, by among other people, John Marsh-Russell. And John Marsh-Russell was to become my PhD advisor that same year that this paper appeared on the archive. And I've been working on this idea ever since, essentially on and off with some other things. And in this paper, they proposed many ways in which axions of different masses can be probed using astrophysics and cosmology. And we're going to meet all of them in the course of this talk. But just to set the context, if you haven't come across this idea before, it's a very, very popular paper. It has 1,500 citations, and its citations are sort of rising year on year. So that's why I thought it's timely to give a talk now and say what's happened in the intervening 14 years. So the Axiverse in 2023, I'm going to use the same mass scale and probes to discuss it. I'm going to talk about linear and quasi-linear cosmology, extending all the way from 10 to the minus 33 electron volts up to around 10 to the minus 20 electron volts in mass for the axion. I'll tell you about some hints, possibly, for the presence of very light axions with mass around the Hubble scale today, due to rotation of the CMB polarization. I'll tell you about some advances that we've made in understanding axions of particular mass in this range around a few times 10 to the minus 20 eV, what's called fuzzy dark matter. I'll tell you about black hole superradiance. I'll tell you about some interesting work that me and a few other people have been involved in recently with heavy sort of KV mass axions and how they decay, and how this is also quite a generic prediction of this kind of model. This goes under the category of freezing. And I'll talk about some unexpected and new developments in cosmology along the way. I won't have any time to tell you about apart from in one slide at the very end, about the advances in direct detection of axions and how this is also probing up to 10 orders of magnitude in mass. So let's get started. I'm going to start with linear plus plus, by which I mean linear, quasi-linear, and almost non, and sometimes completely non-linear cosmology, which is related to the proposals to probe the matter-power spectrum in the original Axiverse paper. So very light axions, making up just a few % of the dark matter density, can show up in their effects on the cosmic microwave background anisotropies in a way that's distinct from the standard lambda CDM model. On the left-hand panel, I'm showing the effect of axions with masses larger than 10 to the minus 27 electron volts. That's roughly the mass scale of matter radiation equality. And here you see the effect of changing the axion mass. So when the axion is at this limit, 10 to the minus 27 electron volts, and it's all of the dark matter, the CMB anisotropies in this dotted red curve have a very different damping tail structure than in the case where you take the mass to infinity, where it agrees with lambda CDM. And the measurements here are from the Planck, I think it's Planck 2012 data on this particular figure. On the other hand, for lighter axions, less than 10 to the minus 27 electron volts, these guys change the distance to the surface of last scattering and change the evolution of gravitational potentials in between the surface of last scattering and us. And what that does to the CMB anisotropies is it changes the position of the first peak and changes the shape of what's called the Sachs-Wolf plateau. And in this case, the results return to lambda CDM in the limit that the mass goes to 0. In that case, the axion behaves like a cosmological constant, and we've recovered the green line whereas in the left-hand figure, the mass going to infinity recovers the limit of cold dark matter. The physics that's going on here is that the damped motion of the axion field at early times behaves like dark energy, and this leads to a different, and this early dark energy effect, or late dark energy effect in the case of low masses, leads to a different expansion rate from the lambda cold dark matter model, which changes the Silk damping scale at large multipoles and changes the Sachs-Wolf effect at low multipoles. This is something that wasn't in the original Axiverse paper, Axiverse proposal, but is something that turns out to be a very strong probe of these very light axions. So you can sort of summarize the constraints in a figure like this. What these effects on the CMB do is they limit the contribution of very light axions to the total dark sector abundance. So here at the constraints go between 10 to the minus 32 electron volts and about 10 to the minus 25 electron volts, and here the red region is allowed. So you see that across this range of covering about 7 orders of magnitude in mass, the axion these light axions are constrained to be less than about 2% of the total dark matter abundance. When the mass goes to infinity, the constraints go away and you're allowed to be all the dark matter. And when the mass goes to 0, with the particular normalization I've chose, you are allowed to be all of the dark energy. What's been happening since 2014 is we've had, so the cosmic microwave background is wonderful because it's linear. But since 2014, we've been working on advances in quasi-linear and non-linear modeling of structure formation and cosmology of axionic fields, using things called halo models, the effective field theory of large-scale structure, and emulators. And these new tools going into the quasi-linear and non-linear regime allow us to extract precision limits on axions from smaller and smaller scales and from more cosmological probes. And moving to smaller and smaller scales corresponds to moving to larger and larger masses. That's because the scale in the problem is essentially the dark matter de Broglie wavelength. So smaller scales correspond to smaller de Broglie wavelength, larger axion masses. And here's an example of the progress that's been made in this field since 2009. In the original Axiverse paper, it was predicted that this de Broglie wavelength in the axion field leads to a suppression in P of K. P of K is the matter power spectrum, the Fourier transform into two-point correlation function to density. And so here you see the density mode K plotted, and at some small values of K, large scales, it's around 1. And then if you introduce a few percent of these light fields, it leads to a suppression in the clustering, in the matter clustering, which becomes saturated at some scale called the gene scale, and then the suppression levels out again when this small fraction of dark matter is no longer clustering at all. Now, what does that look like today? Today, that looks like this. So here I'm showing a figure from a paper I was involved in earlier this year with Kia Rogers and a number of other people, and I'm showing the power spectrum multipoles. So in order to deal with things like redshift space distortions, we tend to take multipoles of the power spectrum. So here there's the power spectrum monopole, quadrupole, hexadecapole, and then the so-called real space power spectrum, where real space means real space rather than redshift space, not real space rather than K space. And the data points are from the baryon acoustic baryon oscillation spectroscopic survey data release 12. And the models here are constructed using the quasi-linear model known as the effective field theory of large-scale structure. And what you see is in the solid line, it's a model with some fixed small amounts of axions here, 3% at 10 to the minus 25 eV. And the solid line goes through the data. So they cannot distinguish 3% of light axions from none. But if I turn up the density of light axions to omega AH squared of 0.09, you see that the power spectrum multipole, the monopole drops off at large K. And that is the same effect that's sketched out very roughly in the left-hand plot from the original Axiverse paper. But now when we want to actually extract the constraints, do it using these techniques from real data, we use all kinds of different public codes, axion camp, which I've been involved in, multi-nest for sampling, cosmosis for likelihoods, and codes like patch or class PT to do the quasi-linear and non-linear modeling. Another key advance that has happened in the cosmology of these light axions, which really happened since 2014, is that we now understand what the cosmic web looks like, including the wave effects of light axions at masses of around 10 to the minus 22 eV. So the first papers to really explore this were by Suyu Shive and collaborators in 2014. And I'm just showing one example of slightly more recent work by Philip Marsh in 2019. So here, this is now the fully nonlinear cosmic web simulated using the Schrödinger-Poisson equations. And there is a dark matter halo here, another dark matter halo here, joined by filaments. This is as we would expect in cold dark matter. But if you actually look at the filaments now, there are interference patterns in the filaments caused by the wave nature of the dark matter. And zooming into halos, there is a turbulent structure and the formation of a core in the center. Now, from these simulations, something that wasn't expected, I think, is that we've had a new and deeper understanding of the nonlinear of the axion field. And Yoram Dima-Levkov has been pretty instrumental, I think, in driving some of this understanding, along with collaborators Panin and Tkachev. And what we've learned about condensation, how the wave effect inside these halos can lead to a form of classical Bose-Einstein condensation, and also about how the turbulent nature of the waves inside halos lead to relaxation effects. And the formation of the cores in the center, something that goes by the name of a soliton or an axion star, I think was also rather unexpected, the sort of dramatic nature of this formation. And there's a lot of new phenomenology coming from these solitons. I'm now going to give you a quick tour of cosmological constraints. And while I go through listing them, I'm going to show you a nice movie. So if we assume that ultralight axions are all of the dark matter, then we can get a wide range of astrophysical observables to constrain to put a lower bound on the mass that is allowed, that's consistent with data, that becomes like cold dark matter. But we need to, in order to move further than what I will list here, we need to understand the nonlinear models in the case of mixed dark matter to test whether axions are some small components. So I'm going to show you, while I list the constraints, a movie looking at the time series dynamics inside a dark matter halo composed of ultralight axions. So one limit that I was involved in extracting relatively recently is if you use the dark energy survey with lensing correlation function, we're able to place a lower bound than the particle mass of 10 to the minus 23 electron volts. And this is using I would say only quasi-linear scales, and it doesn't involve any degeneracies with unknown baryonic physics, which is why this is quite a robust limit, although it's by no means the most powerful. Inside the Milky Way galaxy, these relaxation effects that I think people didn't foresee, certainly in 2009, as being so powerful. Lam Hui and many people since have shown that too much relaxation limits the particle mass from below to be about 10 to the minus 22 eV. Similar limits of around 10 to the minus 22 eV and 10 to the minus 21 eV can be derived from the formation of high redshift galaxies and the formation of Milky Way satellites. Going to even more nonlinear scales, but now degeneracies, for example, with baryonic physics, one of the most powerful limits from cosmological observable is from the Lyman forest flux power spectrum, the strongest one having been derived by Keir Rogers and Hiranya Peris, and this uses the tool of an emulator, which I talked about, so training the observable against a large number of simulations in order to do the statistics. And then finally, one of the most powerful, strongest limits on the mass is around 10 to the minus 19 electron volts, and that is related to the survival of the young star cluster in the ultra-faint dwarf galaxy Eridanus 2. And this limit is, so the last two limits, Lyman-Alpha Forest, comes from the matter power spectrum step that I showed earlier, whereas this more powerful limit from Eridanus 2 comes from the turbulent relaxation effects that, as I said, I think were not foreseen in the original Axiverse paper. Okay, so moving on into our constraints, the next region of the original Axiverse plot I want to direct you to is constraint on decays. If you remember, this appears at relatively high axion masses in the original figure, up to around, say, a GeV. And the way that this has matured in recent years is we've learned how the production of such heavy axions can be thought of as generic due to this process called freezing. So two papers that explored this in the last year were these two. One that I was involved in, published in JCAP by the Gambit collaboration, and then one published in PRL by another group. And these appeared on the archive within a few days of one another. So the physics that's going on here is that the axion-like particle, this time relatively heavy, KV, MEV, GeV, is coupled to photons via the standard axion to two-photon vertex. And then in the early universe, even if there are no axions present initially, axions can be created via the Primakov process. So, for example, here I have an electron, and the electron interacts with a photon by exchange of another photon, and the photon converts into an axion in the presence of this field due to the electron. And in the top, I'm showing the fraction of dark matter that would be produced by such a mechanism if the axion was stable, as a function of the mass, both for different masses, and as a function of the reheating temperature. Now, the way in which these limits depend, the way in which the dark matter abundance depends on the reheating temperature, might make you think that this can't be a model-independent bound on axions. However, since we know that there is a lower bound on the reheating temperature of around 5 MeV in order to explain Big Bang nucleosynthesis, we know that we know that the universe was hot, at least at temperatures of 5 MeV. Setting that as a lower bound on the reheat temperature really allows you to set a lower bound on the abundance of heavy axions. So here, let's just set the reheating temperature to 5, and you see that axions with mass of around 1 MeV would then be produced and make up around 10 to the minus 4 of the dark matter. Now, these axions happen to be unstable by the same interaction, the axions to photon vertex. So now you have a decaying dark matter model. And constraints on decaying dark matter are remarkably strong. And KV to GV dark matter that decays is excluded, even if it makes up only around 10 to the minus 10 of the energy density of the universe, and even if its lifetime is in fact longer than the age of the universe, because there's just so much dark matter that there is still some decaying. So let's have a look at those constraints. And the constraints look like this. So here is the axion-photon coupling, and here is the mass measured in KV. And the colored regions are regions that are excluded by this irreducible freezing contribution when we set the reheat temperature to its lowest possible value, produce that dark matter and allow it to decay. And you see that quite large regions covering many orders of magnitude in coupling constant and mass can be excluded, and the constraints extend quite a lot further below some of the other constraints and axioms here, for example, horizontal branch stars, or from supernova 1987A. And looking at the axion-photon coupling here, the constraint, for example, from X-rays extends down to an axion-photon coupling with 10 to the minus 15 inverse GeV. If we convert that with some sort of standard relation into the equivalent decay constant, it tells us that the axion decay constant has to be larger than about 10 to the 13 GeV. Now, I want you to remember to keep that number in mind when we come to some string theory models at the end of the talk. Okay, the next limit the next method to probe axions I want to review is black hole superradiance. So what is black hole superradiance? Black hole superradiance, the picture to have in mind is what's called the Penrose process and the black hole bomb. So we now imagine we're looking at a Kerr black hole, and the Kerr black hole has an inner horizon, an outer horizon, and an ergo region. And in the ergo region, anything that falls into the ergo region has to co-rotate with the ergo region. So if we drop a particle in with positive energy, and then cause that particle to somehow split in half, Penrose had in mind, literally like a rocket that drops something up at the bottom. Then because it is co-rotating, the particle that's dropped in falls in and goes to negative energy, and then the particle that split in half is kicked out with larger energy, E3 greater than E1. This is a classic superradiant process, and this can be made to repeat over and over if we were to put a mirror around the black hole. So how does this relate to axions? So for an axion, what this process looks like is an instability of the Klein-Gordon equation on the Kerr background spacetime. So we write down the equation of motion, the Klein-Gordon equation, and compute box on the Kerr background metric. In the non-relativistic limit, and in some special coordinates called tortoise coordinates, one can write down an effective Schrodinger equation for the modes of this axion field, evolving in some effective potential that's given by the bare potential of the axion, and some effective potential due to the gravitational potential and angular momentum of the Kerr black hole. And the potential sort of looks like this. There is an angular momentum barrier, a potential well for bound states in sort of intermediate radii, and then going towards the black hole horizon at tortoise coordinate 0. And the way this relates to the Penrose process is that if there's some scalar field here in the potential well, and it has the right wavelength, then it can tunnel through the barrier, which is equivalent to dropping some of itself in, but then it comes back to the mirror, it's a bound state, and the process repeats over and over. Quantum mechanically, this is just the fact that this effective Schrodinger equation has some negative eigenvalues, which lead to exponential growth. So bosons, and this works for any boson, not just scalars, can extract spin from astrophysical black holes. In order to balance the energy, the black hole has to lose some spin. If the superradiant rate, the rate of this process given by the negative eigenvalue, is larger than the rate of any astrophysical process. So this means that if resonant bosons exist, black holes with high spin that are resonant with these bosons should not be observed. But we do observe some highly spinning black holes. So here I'm showing, for example, the measured mass versus spin, dimensional spin A star of a selection of black holes. And look at, for example, LMCX1 and M33X7, which have confirmed high values of the dimensional spin. Now, the superradiant process forbids black holes from existing in any region that looks like this one drawn here. So what's happening in this animation is I'm showing what the forbidden region looks like as I vary the axion mass, which is given by mu here and shown by the color of the region. If the forbidden region overlaps the observed black holes, this means that the model should be excluded. So then in the right-hand panel, I'm computing the exclusion probability, which is related to the marginal likelihood, as a function of the mass. And you see that when the overlap region goes away from the black holes, the exclusion probability goes to 0. When the region that should be forbidden overlaps the observed black holes, the exclusion probability goes up to 1. So what I did with a graduate student in 2018 was apply this idea to a catalogue of all the black holes we could find or we could get our hands on data for, and compute the region of excluded axion masses covering all of these black holes. So we looked at sort of stellar mass-ish black holes with masses of around 10 solar masses. They exclude axion masses in the range 10 to the minus 11 to 10 to the minus 13 eV. We also looked at supermassive black holes with masses around 10 to the 6 to 10 to the 8 solar masses. The spin measurements there are slightly more unreliable, but these exclude axion masses between 10 to the minus 16 and about 10 to the minus 19 electron volts. And there's a gap, a rather interesting one, I think, in between 10 to the minus 13 and 10 to the minus 16 eV. And that's because there are no known intermediate mass black holes, where by intermediate here I mean around 1,000 to 10,000 solar masses with measured spins. And I call this the 1 Hertz axion window, because if you convert 10 to the minus 15 V into SI units, it is 1 Hertz, the Compton frequency of such an axion. One thing that one has to take into account with superradiance is that the axion actually has quartic self-couplings. And the presence of the quartic self-couplings mean that the superradiant process is not stable, and the cloud of axions that is set up due to it can become unstable in a process called the Bose-Nova. So the 2-to-2 scattering of the axions that build up in this cloud around the black hole by extracting its spin, if the 2-to-2 scattering has a rate that is larger than the superradiant rate itself, the rate at which the cloud is growing, then the two compete and the superradiant process is shut off. So here I'm showing the constraints that you would, the excluded regions marked in coloured as a function of axion mass, labelled now by the decay constant, which sets the strength of the quartic self-coupling. So you see that in the stellar domain, the constraints, as I said, go from 10 to the minus 13 to 10 to the minus 11 eV, and they apply for decay constants as small as 10 to the 12 GeV, whereas in the supermassive black hole domain, the constraints only apply for decay constants larger than about 10 to the 15 GeV. So, as I just said here, the approximate region, if you box it off in decay constant, is stellar black hole constraints apply F's larger than 10 to the 14 or so GeV, and supermassive black hole constraints apply for F larger than around 10 to the 16 GeV. Okay, moving on to the next probe listed in the Axiverse paper is cosmic birefringence, which they refer to by the name CMB polarization. So what is birefringence? Birefringence is rotation of the polarization state of the cosmic microwave background by the vacuum. In this case, the vacuum being the motion of the axion field. So we can picture this, the initial polarization states at the CMB here are shown in two modes called E and B, which are the sort of the Stokes parameters, the E mode being the pure divergence mode, and the B mode being the pure curl mode. And if the polarization is rotated as the light goes from the surface of glass scattering to us, then any rotation of the polarization angle mixes up these pure divergence or pure curl states with one another, and it's characterized by a rotation angle beta. Now, an analysis done in 2020 by Minami and Komatsu has claimed to actually detect this effect in the Planck cosmic microwave background, and measurement of the rotation angle around 10 to the minus 3, 5 times 10 to the minus 3 radians. And the way that was done is that the absolute polarization angle was calibrated by cross-correlating the CMB with the measurement of the Milky Way, where the Milky Way is presumed to be unpolarized. And this allowed an absolute calibration of the polarization angle, and thus a measurement of any possible rotation. Now, this analysis has been looked at further by the Planck collaboration themselves, and the effect is seen to be there. And moreover, the dependence of the effect with the size of the galactic mask, because one has to mask out the galaxy in order to get the pure cosmic measurements and then add the galaxy back in to do this cross correlation. And the dependence of the result on the size of the mask appears to be consistent with a signal of cosmic origin. Now, I'm not an expert on this, so and you see, it's only a sort of 2 and a bit sigma measurement, but nonetheless, it's tantalizing because such a rotation can be caused by an ultralight axion. So the ultralight axion phi couples to electromagnetism via this operator here, FF joule, where F is a Faraday tensor, and the joule has its indices raised with the epsilon tensor. This interaction leads to a rotation angle beta, which is just given by the coupling constant g times the integral of the axion field, of the change in the axion field along the line of sight. So eta is the conformal time along the line of sight from the CMB to today. So the axion field, what it does is it starts off its life in the early universe at some constant value set by spontaneous symmetry breaking, and then when the mass of when the Hubble parameter drops below the mass of the axion, the field starts to oscillate. So if the field is heavy and it is oscillating already at the time of the CMB, this integral basically cancels and there's no birefringence effect. However, if the field only begins oscillating at some time between the CMB and today, then the integral has non-zero support. So this fixes the range of axion masses where this effect can happen to masses between the value of the Hubble parameter CMB, which is about 10 to the minus 28 eV, and the value of the Hubble parameter today, H0, which is about 10 to the minus 33 EV. So there's a relatively narrow range of axion masses that can lead to this birefringence effect. And birefringence, because it's probing the axion photon coupling, it can also be synergistic to direct searches for axions. And I'll tell you briefly just about 2 of those. So here's a work by Fujita et al. 2021, where they enforce the birefringent angle of 0.3 degrees and find what regions of the axion mass and coupling space can cause that rotation angle. And it depends on the initial value of the axion field. And so here they show that if you fix the abundance of the field to be the maximum allowed value from the primary CMB anisotropies that I showed way back in the beginning, then you need some particular value of G. However, if you make the field to have a smaller contribution to the dark matter density, then in fact you only need a larger value of G, which makes sense. And if you make the field, say, 10 to the minus 6, then the value of G you need is roughly 10 to the minus 18 inverse GeV. Something that was missed in the original Axiverse paper is that there is a birefringent effect even for more heavy axions. So even though the field is oscillating and that integral for the homogeneous rotation angle vanishes, there is an overall effect of this, that polarization is washed out by this oscillating axion field. And this allows probes of the axion mass and photon coupling in the range of around 10 to the minus 20 to 10 to the minus 23 electron volts that can surpass, in some cases, astrophysical limits. So here is shown the supernova 1987A limit, for example, in dotted, and the CAST CERN Axiom Solar Telescope in solid. And this is something that has been done by CMB experiments themselves, and these limits are from the Keck collaboration. And lastly, on the point of birefringence, is that an isocurvature perturbation in the ultralight axion, something that is induced from quantum fluctuations during inflation, if that is present, then it induces not just an isotropic birefringence, which is this overall rotation, but some anisotropic birefringence caused by the isocurvature perturbation. This anisotropic birefringence leads to a large angle, so-called BB polarization mode in the CMB, which in many respects mimics the more famous tensor modes caused by inflationary gravitational waves. And this is something that is is known and has been explored by a number of people, but I think there's possibly more to it. And if B modes were ever detected, then I think this could be something that is more actively looked at. Okay, so in the last 10 minutes or so, before we go to questions, I want to come back to string theory. So the whole idea here is called string axiverse, that these axions are predicted by string theory. So what's the status of that? What's been going on in string theory for the last 14 years? And here I'm going to specifically talk about Type IIB string theory on Calabi-Yau threefolds and progress that's been made by my collaborators, Liam McAllister's group in Cornell, and this wonderful bit of code that I'll introduce called CY tools, which is allowing us to make real progress on the string theory side. So, axions in string theory in 2 slides. So, string theory can be described as an effective field theory as 10-dimensional supergravity. And 10D sugra has what are called p-form fluxes. And in Type IIB, the one that we're interested in is the 4-form flux C4. So the 10D action looks like this. This is just like the Maxwell action, F5 wedge star F5. But we decompose the field C4 into harmonic forms. So these are things that will automatically satisfy the equations of motion on the compact space. I can decompose C4 into a harmonic form, omega 4, that lives in the y coordinates in the compact space, and A, which depends on the x coordinates in our 4D space. And the basis of harmonic forms is given by the number of closed 4 cycles, which are also called divisors in the compact space X. So I can write then the axion field A as the integral of the 4-form flux over the divisor on which the harmonic form omega lives. The number of basis elements and the number of basis harmonic forms is given by something called H11, the Hodge number, which is a topological property of the compact space. When we compactify, which just means when we integrate the action at the top over the six compact dimensions, we get a 4D action for massless fields in 4 dimensions, and the massless fields A, the axions, are given by the coefficients of the harmonic form 4-form flux. We have dA, I, Kij, wedge star, dAj. This is a quadratic kinetic term for the axion field. This thing Kij is called the Kähler metric, which is given by the second derivative of the Kähler potential, which is proportional to the log of the volume of the compact space. And V itself is given in terms of what are called the Kähler moduli, which has this sigma component here, which sets the sizes of things, and the axion component AI. And V arises in terms of these Kähler moduli due to something called triple intersection numbers, which are also a topological property of the compact space. The eigenvalues of the Kähler metric, if you just look at the term here, the action, it's clear that the eigenvalues of this K set the scale of the kinetic terms of the axions. The scale of the kinetic terms is what's called the decay constant. And parametrically, the eigenvalues of the Kähler metric go like n Planck squared, the only mass scale in the problem, divided lambda, and then the periodic potential cosine. The cosine sums over all axions, and the potential sums over all instantons. Coefficients inside the cosine are what is called the instanton charge matrix, and that is also something that is a topological property of the compact space. Lastly, the coefficient in this expansion, the instanton scale. So this should be
sorry, question. So you probably mean the last line on this slide is lambda 4, right?
Yeah, that's what I was about to say. Lambda to the 4. Yeah.
Yeah. It's just okay. So this can be much lower than Planck. Yeah, if
exactly.
mass of supersymmetry is below. Yeah. Okay.
Well, so it's not just the supersymmetry scale that plays
the exponent.
Here.
Yes,
the exponent.
Right.
So the scale lambda to the 4 is it's set by the Planck scale and the SUSY scale, but it's exponentially sensitive to the volume of the divisor, and that ends up leading to all this phenomenology of light fields. So this story that I've just told leads us to believe that massive so-called closed string axions from the gravity sector, this is all just from supergravity, are almost an unavoidable consequence of compactifying Type IIB string theory. And as was just pointed out, there's an exponential in the scale in the potential. And this is what was said about this in the Axiverse paper in 2009. These observations I've just made, they said they lead us to believe that all axion decay constants will likely to be close to the gut scale. M goes around 2 times 10 to the 16 GeV. That's because the eigenvalues of K only go like 1 over D. They don't depend exponentially on the size of the cycle. On the other hand, axion masses are exponentially sensitive to the areas of the cycles, so we expect their values to be homogeneously distributed on a log scale. And that's why I've been telling you about constraints going from GeV down to 10 to the minus 33 electron volts, because of the presence of this exponential in the instanton scale. And exponentials in non-perturbative effects are, we should be used to this. This is, appears in QCD and in dimensional transmutation and so on. So what's the new, what's happened here that's new? Well, what's happened that's new is being able to explore this in, real Calabi-Yau manifolds. So how do you construct a Calabi-Yau manifold? Well, every Calabi-Yau you've ever seen a picture of, I imagine, looks like this. And all of those pictures are all pictures of one Calabi-Yau manifold called the Fermat quintic. And the way the Fermat, so Calabi-Yau, 3 folds, 3 complex dimensions, 6 real dimensions, are constructed as hypersurfaces in ambient toric varieties. Now, I'm going to tell you everything I know about that, which is about how the quintic is made, and these are the cases of generalizations thereof. So the way the quintic, this thing here, is constructed is we take 5 complex dimensions, which are homogeneous. We then identify some of those using a scaling relation, which takes us from C5 to CP4 complex projective space. We then define a polynomial in the 5 original coordinates in that complex projective space, which has 1 free parameter due to the scaling symmetry that takes us from C5 to CP4. And that polynomial defines a hypersurface, which now has 3 complex dimensions, and in the ambient toric variety CP4. So these are Calabi-Yau hypersurfaces. They're defined by these scaling relations and polynomials. So these can be constructed in complete generality using something called the Kreuzer-Skarke database. So the Kreuzer-Skarke database gives us all possible so-called 4-dimensional reflective polytopes, of which there are 4 times 10 to the 8. They are labeled by H11 and H12, these topological numbers in this plot here. And that these relations, H11 and H12, refer to the number of scaling relations that that you need to go from the homogeneous space to the ambient toric variety. Then, if one does what is called triangulation of these polytopes, this gives you all possible 4-dimensional ambient toric varieties. And there is then a unique polynomial that allows you to construct a Calabi-Yau in that ambient toric variety. with a number of Kähler moduli given by the number of scaling relations that took you to that compactified that toric space for you. And this might all sound crazy, but there's a finite number of reflexive polytopes, and there's one which has the largest possible H11, which is the largest number of axions. That's 491. And here, using this thing called CY tools, I have done a triangulation of 491. It's described by something called the GKZ elements, and I can plot them. And this is all automated fun. And even if you're me and you don't know, and the understanding of the mathematics here is rudimentary at best, you could play around with Calabi-Yau manifolds using this CY tools. So, and here's just some statistics about that. But from the axion point of view, we get the charge matrix, which is unique for the polytope. We get the Kähler metric, which is fixed by the Calabi-Yau. And then the location of the saxion, the modulus, has to be fixed somewhere where all the volumes of everything are larger than 1 in string units, so that you're in the regime where you can trust supergravity. And what's interesting to note is that this one polytope with H11 equals 491 is known to have more Calabi-Yaus associated to it than the entire rest of the database put together. And there's an upper bound in the number of Calabi-Yaus from that polytope of 10 to the 428. So there's a vast number of Calabi-Yaus that can be constructed this way. And with this tool, CY tools, we are able to construct them and construct the axion properties. So this is what the axion properties look like. So here I'm constructing a Calabi-Yau and finding the vacuum of the axion potential and extracting the masses and the decay constants. The axion masses spread from almost the Planck scale, 10 to the 27 electron volts, down to below the Hubble scale, 10 to the minus 33 electron volts. They span a log scale, as was predicted in the Axiverse paper. But it's not quite scale invariant. The sort of universal mass spectrum at large Hodge number has what I would call a blue tilt, where there are slightly more fields at large masses than there are at small masses. So maybe the phenomenology of the heavy axions could be more important than the light ones. Now, the spectrum of the decay constants actually is very different from what was talked about in the original Axiverse paper, although it starts off at low Hodge number around the gut scale. As soon as you go to large Hodge number, which is most of the Calabi-Yaus, the decay constants get smaller and smaller and smaller, and they have a log normal distribution. So at large Hodge number, large number of axions, the decay constants are small. This is now my last slide on what's been going on for the last 14 years. Is using these tools, we can now put real constraints on the Axiverse, on Calabi-Yau vacua. So what I'm just going to show you now is we took an ensemble of 100,000 Calabi-Yaus, and we did all of them with Hodge numbers up to 5, 100 Calabi-Yaus per Hodge number to 176, and a few Calabi-Yaus per Hodge number all the way up to 491. And we were able to exclude some of these Calabi-Yaus using black hole superradiance. And in this sample, which we believe is sort of representative, we exclude up to 50% of all of the Calabi-Yaus up to Hodge numbers of around 200. And then at large Hodge number, we don't exclude anything. But the constraints depend on here 3 different lines where you are in the moduli space. And if you're saying large values of the moduli, then the constraints are much weaker. This is the first, I think, application of the idea in the original Axiverse paper called cohomologies from cosmology. A constraint on the cohomology, the Hodge number, from cosmological observation. The limits are driven by stellar black holes with well-measured spin, and the trends can be easily understood by the trend in chaometric eigenvalues and axion decay constants. I don't have time to tell you about the strong CP problem, And now I'm just going to do a quick summary of what I think the future of this program holds. First of all, the future of the cosmological probes. So this is a very busy plot. This is meant to show you how active this field is going to be in the next 10 years. So the solid regions are things that are excluded by stuff I've talked about, the CMB, black hole superradiance, Eridange 2. The open regions are things that are going to be done with future cosmological observables, the Square Kilometre Array, CMB-HD, CMB-S4, the Rubin telescope. These limits are going to extend the constraints on the axion energy density down into this region here, marked with a black dotted line. The black dotted line is what you would predict, where you would expect the axions to be if they had a gut scale decay constant. The original prediction of the in the Axiverse paper. The limits we currently have do not test that prediction, the gut scale prediction, except in a few places at high mass. But we will now, in future, we will be able to extend these limits to test this gut scale prediction over, I think, around 8 orders of magnitude in axion mass. And this is all to do with the advances in precision cosmology and modeling of multi-component dark matter in the quasi-linear regime. The other thing that will happen is the QCD axion will be found. You may have seen plots like this. This is the axion mass versus photon coupling, all current constraints in solid, projected constraints in light. Lots of experiments coming online in the next 10 to 20 years, which will find the QCD axion if it's there. An easier way to read this is this figure here, which just shows the QCD axion mass existing limits in green and planned limits in red and blue, which should cover almost all of the allowed QCD axion mass from kilohertz to terahertz. And finally, I think there will be more advances on Calabi-Yau manifolds, and this is something that I hope to publish later this summer with the Cornell group. And I can tell you some preliminary observations about that. Axions above the QCD line, more strongly coupled to the QCD axion, require that hypercharge in the UV lives on some large cycle in the Calabi-Yau. And this means that U1 would have to complete into an asymptotically free non-gut group. This might sound quite technical, but if we find axions that are more weakly coupled than the QCD axion, then it tells us something about the realization of U1 in Calabi-Yau manifolds. Birefringence, we can make it happen in explicit constructions with the visible sector, but the angle is slightly too small to explain the current anomaly in Planck. The prospect of freezing and decay of heavy axions leads to very strong limits, especially if the reheating temperature is high. Here is a preliminary figure. Fraction of excluded Calabi-Yau manifolds in some non-representative sample. But the fraction of excluded manifolds becomes very large, approaching 100%, if the reheat temperature is large. But even at low reheat temperatures, the constraints are still relatively strong, 65% of manifolds excluded. Axion reheating may occur, but there's a large laundry list of things we need to look at to do with dark sectors, explicit orientifolds of Calabi-Yaus, and many other things. And with that, I will leave you with my summary slide, and I'll happily take some questions.
Thank you. Are there any questions?
Can I ask about the pi to 4 instability in the case of black holes in the which kind of happens in the cloud of axions around them? So how is that a constraint, an experimental constraint? How do you see it?
Right. So okay. So what happens is as the superradiant cloud grows, and once it reaches some critical vat size, then the 2-to-2 rate becomes large. And what that means is that it stops the superradiant process, so that let me try and explain it. I showed that there's a region of black hole parameter space that is excluded. The mass versus spin. Now, if you have the 2-to-2 process, the region of mass versus spin that is excluded gets smaller because you're less efficient at extracting spin. Now, I think that much is clear. Or rather, that much people would agree on, that something happens that can compete with superradiance. As soon as there is a process with a high rate, you're no longer sure that superradiance occurs. Now, what happens when you reach the end point of this instability? I believe there is some debate whether you just reach some steady state where the scattering and the superradiance are in equilibrium, or whether there is actually, and then there wouldn't be an observational signature other than the spin of the black hole saturating. Or I think other people believe that perhaps the cloud grows and becomes unstable and collapses and then explodes again into relativistic axions. Now, I would vote for the second thing happening based on what we know about axion stars, right? That you take an axion star, you increase its occupation number enough, and then, as you showed, the axion star collapses and then explodes. I think the same thing would happen for a superradiant cloud.
Yeah, but that would be
I believe it hasn't been proven.
But that would be unobservable, right? You couldn't observe this relativity axions.
Well, if they interacted with photons and they went through a magnetic field on the way, they would turn back into they could be turned back into photons. So yeah, I think that maybe the boson-over explosion does happen, and it could be observed if those axions converted back into photons.
Okay, thanks.
Maybe I missed this. You discussed Calabi-Yau compactification, but maybe what about any alternatives? There could be some, I don't know, brains or whatever. What is known about similar story there?
Right. Yeah. So everything I said was about Calabi-Yau as a Type IIB. So what else could happen? Axions are still generically there in the heterotic picture. In the heterotic picture, the axions arise from the 2 form, and things are a lot harder to do because heterotic is a global theory. Type IIB, the matter content only depends on matter lives on brains, whereas in heterotic matter lives on strings, and it's all much harder. But most of the story, I think, goes through for heterotic. Somewhere where we hope that we might be able to make progress is in F theory. So F theory can be understood as a way of addressing strong coupling in Type IIB. But there's a similar story of Calabi-Yaus. They're Calabi-Yau fourfolds, and you can understand the matter content. I believe we might be able to make progress with F theory, or my collaborators tell me so. If it's something like you described, some kind of brain world where one of the extra dimensions is rather than being compact has boundaries. I don't know how the story changes there, and my impression is that not very much is known about string theory on non-Calabi-Yau backgrounds. So I don't know. I honestly don't know.
Okay.
But yeah, I think one could make progress with heterotic and F theory using the tools that I've talked about. Non-Calabi-Yau backgrounds, I don't know.
Yeah, I had in mind, well, there was some, I don't know, type 1 kind of orientifold attempts to construct phenomenology. But anyway, yeah, this is a bit exotic. So Calabi-Yau is indeed more mainstream. Yeah.
There is actually some. One thing to add: there is some that is known about this in M theory. my colleague here, Bobby Acharya, has done some work on axions on G2 manifolds as well, and that does sort of relate to your question about a model with branes, right? Because what is it? M theory on a compact interval is dual to type IIB or something. So there is some progress on the M theory side.
I also have a question about this string axions picture. The question is, how do you make such a small decay constant? So 10 to the 10 GeV, like, is it a large extra dimension, large Calabi-Yau, physically large? And do you have some effects related to large extra dimensions?
So I have a slide on that. Thank you for asking. So the small decay constants, 10 to the 10 GeV or so, that can be explained by this trend that is observed in the volume as a function of the Hodge number. So at large Hodge number, the volume becomes large in string units. And that's because, my basic picture as a non-string theorist is, as you add more and more cycles to the extra dimensions, you have to make them bigger and bigger to fit the cycles in, because we want everything to be at least order 1 in string units. That's what being at the tip of the stretched Kähler cone means.
This is kind of exponentially large, right? Exponentially large, like TV. It could be.
So the volumes here are going up to 10 to the 15 in string units. But when you work out the associated KK scale, the KK scale is larger than F. So the KK scale would still be, I can't remember how the KK scale goes, but it's still large. The KK scale is still large, like 10 to the 10 GeV or so. Now the average decay constant, average eigenvalue of the Kähler metric, scales with the Planck scale divided by v to the power 2/3 once you go to Planck units. So that's where that. So then 10 to the 10 to the power 2/3 Planck scale divided by that is where the 10 to the 10 GeV comes from, and they are exponentially large volumes, but the KK scale remains around the scale of the decay constant. So the KK scale is also like around 10 to the 10 GeV.
So it kind of has very curved, it has high curvature. Okay, thanks. This answers my question. Thank you.
And the volume is 10 to the 10, but then the length scale, of course, is 10 to the 10 over 6 in string units, right? So the length scale is still not that large because it's to the power 1/6.
Okay. Thank you for the talk. Okay, so
thank you much. Okay.
Any further questions? I guess no, right?
Yeah, great. Thanks very much. It's been a pleasure.